Hi, I'm Toghrul. We'll be talking about how to verify properties of linear recurrence sequences and why we might be interested in doing that. In order to motivate our study of LRS, let me begin by the problem of verifying linear loops. Suppose we are consider this program fragment over three variables x, y, z, where the variables are initialized and then updated linearly inside the loop. From this loop, we can derive the sequence Sn of points in three-dimensional space, where the coordinates of Sn are equal to the values of x, y, and z after n iterations of the loop. Then Sn can be computed like this. Let's visualize what the sequence Sn looks like for our particular loop. Once we have the sequence, we might want to ask questions about it. For example, does the sequence ever enter some set S? This is the reachability problem or the loop termination problem, where the guard of the while loop would be the set S. Alternatively, we could ask if the sequence Sn ever enters the set S infinitely often, if it eventually gets trapped in S, if it eventually visits S1 followed by S2, and so on. To have a more concrete example about where do these sets S come from, let's partition our three-dimensional space into four semi-algebraic sets as follows. A plane S1, the half space beneath it, and two regions above it. Let me rotate this picture a little bit. Now suppose we run our loop and record at each step the set in this partition where the values of the variables lie. This way we obtain an infinite world of colors where each color corresponds to one set in our semi-algebraic partition. The problem of verifying linear loops now reduces to the problem of verifying properties of this world. And in this direction, what we ideally would like is the following. Given a linear loop with update matrix M and start values S, semi-algebraic partition of the d-dimensional space, where d is the number of variables, a Büchi automaton A decide whether the infinite world of colors generated by this loop is accepted by the automaton A. So this would subsume all the questions that I have mentioned before about linear loops and much more. What we do in our work is that we show that if we restrict the matrix M to be diagonalizable and the Büchi automaton A to be prefix-independent, then the resulting problem is decidable. Diagonalizable is the standard notion, and an automaton A is prefix-independent if for every infinite word W that is accepted, if we make finitely many insertions or deletions to the word W, the resulting word is still accepted. So one cannot change the acceptance or rejection of the word by making finitely many changes to it. To obtain this result, we use the theory of linear recurrence sequences, and the same analysis also tells us why these restrictions of diagonalizability and prefix independence are necessary. Next, I'll try to elucidate this connection to linear recurrence sequences. Let me begin by considering what kind of sets are allowed to be in our partitions of the d-dimensional space. So a set is semi-algebraic if it can be defined by a Boolean combination of polynomial equalities and inequalities. Hence, semi-algebraic sets are closed under unions, intersections, and complements, and they include all polytopes, as well as the lower dimensional shapes like half spaces, lines, and points. But they can also include curved sets. Let's look at an example. If we're in three-dimensional space and have a single linear polynomial, then we can define a plane or a half space by setting that polynomial to 0 or greater than or equal to 0. But if we have a nonlinear polynomial, then the sets we obtain will not be simple shapes as planes or or half spaces. So now let's look at a concrete model checking example with a concrete semi-algebraic set to see the connection to linear recurrence sequences. Suppose we have this particular matrix M and starting value is 1, 0, 0, and our semi-algebraic partition is created using a single polynomial P. So the three-dimensional space is partitioned into three parts, where the polynomial P is positive, where it is equal to 0, and where it is negative. And this polynomial is P of x, y, z equals x minus y, z squared. Suppose, in addition, we have an automaton A labeled with letters plus, 0, minus, corresponding to which of the three sets in our partition the points in our sequence will be. Then the infinite world of colors we obtain is essentially over the signs plus, 0, and minus. And the model checking problem for this particular linear loop is the following. It is to decide whether the automaton A accepts the sign pattern generated by applying polynomial P to the elements of the sequence S, which represented the values of our variables after n iterations of the loop. Now let's have a closer look at what these values of S are. So here, each column, the first three entries in each column correspond to a value of S. For example, the first one is S0, second one is S1, S2, S3, and so on. So xn is the value of the variable x after n iterations, yn is the value of y after n iterations, and so on. And at the bottom, we have the value when we evaluate the polynomial p at the point xn, yn, zn. So the set in our partition where we will end up depends on the sign of this value. It turns out, and this is the case for all linear loops, the value of xn is a linear recurrence sequence. And in this case, it's going to be xn is the sum of xn minus 2 plus xn minus 3. That, for example, x4 would be a sum of x2 and x1. So 5 would be sum of 3 plus 2. So each element is the sum of two preceding elements, not with one in between. But the same recurrence relation also holds for the values of yn and zn. But the linear recurrence sequences are known to be closed under addition and multiplication. And the value of p evaluated at xn, yn, and zn is simply this. And we can conclude that this value will also be a linear recurrence sequence. What this whole example points us at is the following. Verification of linear loops, especially when there is when the partition that we with respect to which we are verifying is obtained from a single polynomial, is equivalent to analysis of sign patterns of linear recurrence sequences. When we have, of course, when we have more than one polynomial, we're going to have a slightly different situations because we will have one linear recurrence sequence per polynomial defining our semi-algebraic sets. But this situation where there is a single linear recurrence sequence turns out to require all the necessary ideas to solve the general problem and also contain all the difficulties. So going back to our main result, we showed that if we restrict the matrix to be diagonalizable and the automaton to be prefix-independent, then we can verify that loop. In this talk, the concrete result I'll show is the following. Given a linear recurrence sequence UN, a Büchi automaton A, whose edges are labeled with plus, 0, or minus, decide whether the sign pattern of this linear recurrence sequence is accepted by that automaton A. So sign of U1, for example, is positive, 0, or negative, depending on the sign of U1. And diagonalizable linear recurrence sequence, well, I'll explain what they mean, but they essentially correspond to diagonalizable linear loops. Now that we've seen that analysis of sign patterns of LRS is equivalent to verification of linear loops, let me begin to formally define what linear recurrence sequences are. A linear recurrence sequence is a sequence of, say, rational numbers, where each element is a linear combination of d preceding ones. To specify such a sequence, we would need to supply two pieces of information. We would need this linear relationship and the values of first d elements of the sequence. Here's another definition of the same class of sequences. The nth element of the sequence is some matrix M raised to the power n, a 1 by d row vector of rational numbers, multiplied by d by 1 column vector of rational numbers. So this gives us a rational number, and as we increase n, we obtain newer and newer elements. Finally, here's another definition of the same class, but this is the most amenable to analysis. So the nth element is a sum of entries of the following form: a polynomial in n whose coefficients are algebraic numbers, multiplied by lambda I raised to the power of n. So here lambda I is also an algebraic number. So we'll use this form to deploy tools from algebraic number theory and Diophantine approximation to solve the model checking problem for sign patterns of linear recurrence sequences. Here's an example defined in all three ways. So suppose un is equal to this, with the first two elements 4/5 and 7/25. The equivalent in the matrix powering form would be this, and in the powers algebraic number power sum form, we have lambda 1 equal to this number, which is non-real complex, lambda 2 equal to this, and two coefficients, that both of which are equal to a half. And since we're interested in diagonalizable linear recurrence sequences, a linear recurrence sequence is diagonalizable if the matrix in the second form, defining it, is diagonalizable. But we'll see that diagonalizable LRS also have a special form in this power sum shape as well. So now, before moving on to the general verification of sign patterns, let's look at the smaller smaller alphabet. So suppose we only care about whether the linear recurrence sequence is 0 or not. So here we have an LRS, and suppose we abstract it away to two groups, non-zero and 0. So suppose we want to verify this modified sign pattern. The most important theorem in this area is the Shaull-Mayer-Lech theorem, which tells us that this sign pattern is ultimately periodic. So it has a finite prefix, and after which there is a finite pattern that repeats infinitely often. But this pattern is not known to be effectively computable. So we can compute W2, which determines the asymptotic behavior of the sign pattern, but computing W1 is open, and this is known as the Shaull's problem. So this example shows us something that keeps coming up, that analyzing the asymptotic behavior of linear recurrence sequences is often much simpler than analyzing the general behavior. So a side note about Shaull's problem. So one version of it is to compute the finite prefix W1. The second one is to decide if a given linear recurrence sequence is ever 0. So suppose we have computed W2 and it does not contain any zeros. So to be able to decide whether the sign pattern contains a 0 at all, we need to decide whether W1 contains a sign pattern that contains a 0 or not, which we are unable to tell at the moment. And this is equivalent to, in terms of linear loops, deciding whether a linear loop with a guard that is a hyperplane ever terminates. So if we replace the guard, the equality in the guard with greater than or equal to or any other inequality, we obtain a problem in terms of linear recurrence sequences called the positivity problem, which is another long-standing open problem, and it's thought to be even harder than the Skolem's problem. Let's go back to our old alphabet. So suppose we've got a linear recurrence sequence, and this time our sign pattern is either positive or negative or zero. So is this sign pattern also ultimately periodic or not? It turns out that this is not the case, and here's a counterexample. So this LRS simplifies to UN equals cosinus of n theta, where theta is an angle that's not a rational multiple of pi, and this sequence is known to be not ultimately periodic. So we cannot use ultimate periodicity to model check even asymptotic properties in this case. But in our work, we show that we can weaken this notion of periodicity, but still maintain certain desirable properties. So what we show, the main lemma of our work, is that the sign description sigma of diagonalizable sequences is almost periodic. So almost periodicity, what it means, suppose we have a sign pattern. It is almost periodic if for every finite word that occurs infinitely often, the distance between consecutive occurrences is bounded. So everything that happens infinitely often is going to happen within a given bound. And we use this to verify the sign pattern of diagonalizable sequences. So let me formally define what is almost periodic. So an infinite word is almost periodic if for every finite word there exists a p such that either the finite word does not occur in the infinite word after the position p, or the word w occurs in every factor of length p. So we can have one p per finite word. So these words have been studied under various guises, and then they are known also as uniformly recurrent sequences or minimal sequences. Some examples would be ultimately periodic words, of course, then Sturmian words, two Morse sequence, and so on. A typical non-example would be this word. So the letter B occurs infinitely often, but the gaps between consecutive occurrences of B's grow to infinity. So this word is not almost periodic. But so what is so desirable about almost periodic words? There's a result by Semenov that shows that if we have a predicate P whose characteristic word is effectively almost periodic, then the MSO theory of natural numbers with order extended with P is decidable. So this characteristic word is an infinite sequence where it is one at positions where predicate P holds and zero otherwise. But it requires effective almost periodicity. So effective almost periodicity, roughly speaking, means the P in the definition of almost periodicity that I gave is computable. And the almost periodicity of P is used to first prove this result, that if we have a Büchi automaton, and if we run this Büchi automaton on the characteristic word of this predicate, it is decidable whether the automaton accepts this word or not. And if we can solve this problem, then the MSO theory of natural numbers extended with that predicate becomes decidable. So because we do not have effective almost periodicity, we'll have to show our decision procedure manually, so we cannot use the Semenov result directly. But before that, let me try to argue that the sign pattern of diagonalizable sequences is indeed almost periodic. I'll do that for the finite finite word that is only plus, so only the letter plus. So I'll show that if UN is a diagonalizable sequence, then if the letter plus occurs infinitely often, then we can compute a uniform bound D such that within every window of D there's a plus. And we'll do this, the two abstract steps will be, we'll reduce an arbitrary diagonalizable sequence to a much simpler linear recurrence sequence. And then in the end, we'll use a compactness argument to derive the bound. So recall that the linear recurrence sequences could be written in the form that was a sum of powers of lambdas. So if a sequence is diagonalizable, then this form has a particularly simple shape where the coefficients are algebraic numbers. They were allowed to be arbitrary polynomials before. So a diagonalizable sequence can be written as a linear combination of lambda 1s to lambda d's raised to the power n with algebraic coefficients. So what we do here is we group these lambdas into two groups. The dominant part, where we accumulate all the lambdas of the largest modulus, and all the lambdas with smaller modulus we put to the rest. So I call this part dominant part, and then this part the remainder. So the result that we use here is the following. There exists, for a diagonalizable sequence, there exists a point n0, such that from there onwards, the modulus of dn is strictly larger than that of rn. This means that if we want to determine the sign of un, it suffices to determine the sign of dn. This existence of such a result might seem obvious at the first glance, but because, of course, lambda 1s and lambda r's are strictly larger, and when you raise a complex number to power, its modulus also grows. But these algebraic numbers can cancel one another out. So, for example, suppose we have un equals cosinus n theta plus 2 to the minus n, where theta is some angle that's not a rational multiple of pi. Then this would be a linear recurrence sequence, but cosinus n theta can come arbitrarily close to 0. So then whether the sign of un is determined by cosinus n theta or 2 to the power of minus n theta will depend on the speeds of convergence with which these two things can go to 0. So this result is highly non-trivial and uses this bounds on sums of S units and the periodic subspace theorem. But what we are interested in here is that this n0 is not effective. So we know that it exists, but given a diagonalizable linear recurrence sequence, we are unable to compute it. So this non-effectiveness is a reason why we have to use prefix-independent automata. Okay, so now that we know that to know the sign of a diagonalizable sequence, we need to look at only its dominant part, especially because we want to prove that the sign pattern is almost periodic, and for that it suffices to look at the sign pattern after this point n0. So we've reduced the problem to analysis of signs pattern of linear recurrence sequences that are of this form. The C's are algebraic numbers, and lambdas are also algebraic numbers of modulus 1. Why modulus 1? Because in the dominant part, they all have the same length, and we can divide, dividing a linear recurrence sequence by a positive number does not change its sign. So each of these lambdas is a point on the unit circle. And the object that we're interested in is this subset of R products of unit circles that corresponds to all the values that these powers of lambda can take. So observe that when we raise a lambda 1 or lambda 2 or lambda r to a power, because they are on unit circle, essentially we do a multiplication by a fixed angle. This set of powers is not easy to describe, but Luckily, there's a small over approximation. So there is a set T sub lambda that is the subset of this R product of unit circles that is compact, semi-algebraic, and the formulas that describe it can be effectively computed. But most importantly, this T sub lambda is equal to the closure of this set. That is, this set is dense in T lambda. So now that now let's look at we've looked at raising lambdas to powers. Now let's look at this linear combination part. So here let's denote this T lambda by this circle, and then let the whole field circle to be T to the power of R. So recall that we want to show that the distance between positive indices is bounded. So let's define this subset of T lambda. T lambda is the set of all powers of lambdas, such that when we apply F, we obtain a positive number. So if the powers of lambdas land in this red set, then the value of the sequence that we obtain is going to be positive. And this set is an open set. So by retracting this set by lambda, we can obtain another second set of intervals here. These are the set of intervals such that if the powers of lambda land in there, then at the next step, they are going to land in the previous set of intervals, and that means that if the powers of lambda is in this set, then they will be positive in the next step. By continuing this process, we obtain a cover of T lambda. By the way, this process must result in a cover by the density, and because we know that T lambda is compact, this open cover must have a finite subcover. And the conclusion for us here is that if the powers of lambda they land wherever, it will take only finitely many steps until they go into this part of T lambda where the value of the linear recurrence sequence becomes positive. So what I just showed was that the letter plus occurs within a bounded window of time, but this is true in general for any finite pattern in the sign pattern of a diagonalizable sequence. So if we have zeros in the pattern, of course we have to be a bit more careful, because the retraction of an open set in this case is not going to be open. But here we can use Scholer-Meyerlech theorem, which tell us exactly where the zeros are. So now that we have almost periodicity of the sign pattern of a diagonalizable sequence, what we still have to do is to show what to do if we have a prefix-independent automaton and our sign pattern, where we want to decide whether the automaton accepts the sign pattern. So for this, we still need to be able to compute some things about sigma, and the required weak effectiveness can be summarized as follows. If we can decide whether the word W occurs infinitely often in sigma, and if it does, we can compute a bound on the distance between consecutive occurrences, then we can abstract away from the sigma and the linear recurrence sequences and all of this to single procedure inter of sigma that takes a finite word and returns either no or a set of finite words, where the output no means that the word W does not occur infinitely often in sigma, and we obtain k words that are all possible words that sandwich W in the sign pattern. So such set must exist because there is a bounded gap between two occurrences of W. And now the problem we have is to decide, given an automaton and this procedure inter sigma, does the automaton accept the word sigma? And we show how to do this. To summarize, what we showed was that the sign description of a diagonalizable LRS it is decidable whether this sign description is accepted by a Büchi automaton or not. For non-diagonalizable sequences, there are examples where the sign pattern is not almost periodic, and this results in complications. And finally, if we try to remove prefix independence, we run into a Skolem's problem and positivity problem, both of which are long-standing open problems. Thank you.